Hello there. Welcome to Science Verse Before Sleep. Tonight, we're going on a journey together, a journey to the heart of our cosmic home. We're going to explore what lies at the very center of the Milky Way galaxy. And as we drift through this story, let yourself relax. Let your breathing slow and allow the wonders of the universe to carry you gently towards sleep. Imagine for a moment that you could step outside on a perfectly clear night, far from any city lights. Above you, stretching across the darkness like a river of light, is the Milky Way. Billions of stars, shimmering and ancient, forming a band across the sky. The ancient Greeks thought it looked like spilled milk, and that's how our galaxy got its name. But tonight, we're not just looking at the Milky Way. We're going to travel to its center to discover what mysterious force holds all those billions of stars in their cosmic dance. And what we'll find there is something so strange, so powerful, that it challenges everything we think we know about space and time. Let's begin our journey. Part 1. The Hidden Heart. For thousands of years, humans looked up at the night sky and wondered. We saw the stars. We mapped the constellations. We watched the planets move. But we couldn't see the center of our own galaxy. And there's a good reason for that. Between us and the galactic center lies an enormous amount of dust, cosmic dust, made of tiny particles of rock and ice and carbon scattered throughout space. This dust blocks visible light, the kind of light our eyes can see. It's like trying to see through a thick fog. The light just can't make it through. For a long time, astronomers didn't even know that the Milky Way was a galaxy, or that galaxies existed at all. They thought the universe was just our solar system, surrounded by distant stars. The center of everything, they believed, was simply more stars fading into darkness. But in the early 20th century, everything changed. Astronomers began using new techniques to study the sky. They discovered that the Milky Way wasn't just a random collection of stars. It was a vast spiral galaxy with arms of stars and gas swirling around a central point. Our sun, our Earth, everything we know. It's all located out in one of those spiral arms, about 26,000 light-years from the center. 26,000 light-years. Let that distance settle in your mind for a moment. Light, traveling at 186,000 miles per second, takes 26,000 years to make the journey from the galactic center to Earth. If someone at the center of the Milky Way looked at Earth right now, they'd be seeing it as it was in the Stone Age, when humans were just learning to make simple tools. As astronomy advanced through the 20th century, scientists became more and more curious about what lay at that distant center. They couldn't see it with visible light, but they realized they could use other kinds of light. Radio waves, for instance, pass right through cosmic dust. So do X-rays. And infrared light, which is just beyond what our eyes can detect, can pierce the veil as well. In the 1930s and 40s, astronomers began detecting strange radio signals coming from the direction of the galactic center. There was something there, something that was emitting enormous amounts of energy. They called this radio source Sagittarius A because it was located in the constellation Sagittarius. But what was it? For decades, that question remained unanswered. The technology simply wasn't good enough to see clearly what was happening at the heart of the Milky Way. But scientists had theories, and one theory, proposed in the 1960s and 70s, seemed almost too strange to be true. What if there was a black hole at the center of our galaxy? Not just any black hole, but a supermassive black hole. A black hole millions of times more massive than our sun. A cosmic monster lurking in the darkness, pulling everything around it into an endless gravitational embrace. At first, many scientists were skeptical. Black holes were still theoretical in those days. Strange predictions that came out of Einstein's equations, but nothing anyone had actually observed. And a supermassive black hole? That seemed like science fiction. But as the evidence accumulated, year after year, the picture became clearer. Let yourself sink a little deeper into comfort now. Adjust your pillow if you need to. Close your eyes if they're not closed already. And let's continue our journey. By the 1990s, astronomers had powerful new tools at their disposal. Infrared telescopes, mounted on mountains far above the dusty lower atmosphere, could peer through the cosmic dust toward the galactic center. And what they saw was remarkable. Stars, lots of stars, packed densely together, orbiting around a single point. But what were they orbiting? There was nothing visible there, just empty space. Yet these stars were moving incredibly fast, whipping around in their orbits like planets around a sun. A group of astronomers, led by Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute in Germany, began a decades-long project. They would track the movements of these stars with incredible precision. Year after year, they took images, measured positions, calculated velocities. What they discovered would eventually earn them the Nobel Prize in Physics in 2020. The stars near the galactic center were indeed orbiting something, and by tracking their orbits, the astronomers could calculate exactly how much mass that something contained. It's the same principle Isaac Newton discovered centuries ago. The way an object moves in orbit tells you about the mass of what it's orbiting. One star in particular caught their attention. They called it S2. This star has an incredibly close orbit around the galactic center. So close that it completes one full orbit in just 16 years. For comparison, our sun takes about 230 million years to orbit the center of the galaxy. S2 moves fast. At its closest approach to the galactic center, it's traveling at about 3% of the speed of light. That's about 5,000 miles per second. Imagine that speed, faster than anything humans have ever built. And what S2 revealed was stunning. By carefully tracking its orbit, astronomers calculated that whatever S2 was orbiting had to be about 4 million times more massive than our sun. 4 million suns, all packed into a region smaller than our solar system. There was only one explanation that made sense: a supermassive black hole. They gave it a name: Sagittarius A star. Sagittarius A star became the official designation for the supermassive black hole at the center of the Milky Way. But naming it was one thing, understanding it was another. Let your mind wander now through the darkness between stars. Feel yourself drifting, weightless, through the cosmic ocean. And as you drift, let's explore what Sagittarius A star really is. To understand Sagittarius A star, we need to understand black holes themselves. And to understand black holes, we need to think about gravity. Gravity is the force that holds you to the Earth right now. It's what makes things fall when you drop them. It's what keeps the moon orbiting Earth and Earth orbiting the sun. Gravity is one of the fundamental forces of nature, a gentle pull between every piece of matter in the universe. The more massive something is, the stronger its gravity. Earth's gravity is stronger than the moon's because Earth has more mass. The sun's gravity is much stronger than Earth's because the sun is much more massive. Now imagine something with an enormous amount of mass, but compressed into an incredibly small space. The gravity near such an object would be unimaginably strong. That's what a black hole is. A black hole forms when a massive star runs out of fuel and collapses. The star's core, which had been held up by the outward pressure of nuclear fusion, suddenly has nothing to support it anymore, and gravity, unopposed, crushes it down. Down and down it goes, smaller and smaller. The matter gets compressed to densities that are almost impossible to imagine. And at some point, something remarkable happens. The gravity becomes so strong that nothing can escape, not even light. You see, light is the fastest thing in the universe. Nothing can travel faster than light. But if gravity is strong enough, even light can't overcome it. Light that tries to escape from a black hole gets pulled back in, like a ball thrown upward that falls back to Earth. And that's why it's called a black hole. The hole itself doesn't emit any light, because light can't escape. It's a region of pure darkness in space, the boundary around a black hole. The point of no return where even light can't escape is called the event horizon. Cross the event horizon and you're gone forever. You can never come back. You can never send a signal out. You've fallen out of the universe, in a sense, into a place where space and time behave in ways we can barely comprehend. Now, Sagittarius A star isn't just any black hole. It's what astronomers call a supermassive black hole. These are black holes that contain millions or even billions of times more mass than our sun. And almost every large galaxy has one at its center. We don't fully understand how supermassive black holes form. They might have grown gradually, swallowing gas and stars over billions of years. Or they might have formed in the early universe, when everything was denser and closer together. It's one of the great mysteries of modern astronomy, but we do know they're there. And Sagittarius A star, with its 4 million solar masses, is our nearest example. Let yourself breathe slowly now, in and out. Feel your body relaxing, your mind quieting, and let's continue deeper into this cosmic mystery. Part 2. The evidence we can't see. Here's something fascinating. We've never actually seen Sagittarius A star directly, at least not until very recently. And even then, what we saw wasn't the black hole itself. How do you observe something that doesn't emit light? How do you study something invisible? The answer is, you look at everything around it. Think of it like this. Imagine you're in a dark room and there's an invisible person moving around. You can't see them directly, but you can see the things they affect. Maybe they brush against a curtain and the curtain moves. Maybe they step in a puddle and water splashes. Maybe they breathe and you see their breath in the cold air. That's how we study black holes. We look at the effects they have on everything around them. Those stars orbiting the galactic center, like S2, they're one kind of evidence. Their orbits tell us something massive and compact is there. But there's more. Sagittarius A star is surrounded by hot gas. This gas is slowly spiraling inward, pulled by the black hole's gravity. As it spirals, it heats up. It gets incredibly hot, millions of degrees. And when gas gets that hot, it emits X-rays and radio waves. We can detect those X-rays and radio waves. We can study them, analyze them, learn from them. And what they tell us is that there's something at the center of our galaxy that's heating this gas to extreme temperatures, something with immense gravitational power. But here's where it gets really interesting. In 2022, astronomers released the first actual image of Sagittarius A star. Not just data, not just calculations, but an image. A picture you could look at with your own eyes. How did they do it? They used a technique called very long baseline interferometry. It's a complex name for a clever idea. Basically, they linked radio telescopes from all around the world. Telescopes in Hawaii, in Arizona, in Chile, in Antarctica, in Spain, and they combined the data from all of them. By working together, these telescopes acted like one enormous telescope, as big as the entire Earth. And what they saw was a ring of light around a dark center. There was a glowing ring. The ring was made of hot gas, spiraling around the black hole, shining brightly, and in the middle, a shadow, the shadow of Sagittarius A star itself. You see, the black hole doesn't emit light, but it bends the light around it. Light from the hot gas follows curved paths through the warped space near the black hole. Some of that light reaches us, and some doesn't. The result is that we see a bright ring surrounding a dark region, the silhouette of the black hole against the glowing gas. It was one of the most remarkable achievements in the history of astronomy, an image of something that, by definition, is invisible, an image of darkness itself. Let that image rest in your mind for a moment. A ring of light, glowing orange and yellow in the radio wavelengths, and at its center, darkness, pure, absolute darkness, the event horizon of Sagittarius A star. Now let's return to those stars, the ones orbiting close to Sagittarius A star, because their stories are incredible. Imagine you're a star, born millions of years ago in the crowded center of the galaxy. You're surrounded by other stars, thousands of them, all packed into a relatively small space. And at the center of everything is the black hole, invisible but undeniably present. Your orbit takes you around the black hole again and again. Maybe your orbit is wide and leisurely, taking thousands of years to complete. Or maybe, like S2, your orbit is tight and fast. As you orbit, you experience forces that stars in the quieter parts of the galaxy never experience. The gravity near the black hole is so strong that it affects time itself. This is one of the predictions of Einstein's theory of general relativity. Time doesn't flow at the same rate everywhere. Near a massive object, especially something as extreme as a black hole, time moves more slowly. We call this gravitational time dilation. For the star S2, this effect is measurable. When S2 is at its closest approach to Sagittarius A star, time for that star is running slightly slower than time for us here on Earth. Not by much, just a tiny fraction, but enough that astronomers can detect it with their instruments. If you were somehow standing on a planet orbiting S2 and you looked back at the rest of the universe, everything would appear to be moving slightly faster than normal. Clocks would tick faster. Stars would age more quickly. It's as if you'd stepped into a pocket of slowed time. The stars near Sagittarius A star also experience something called gravitational redshift. When light climbs out of a deep gravitational well, it loses energy. It shifts toward the red end of the spectrum. Astronomers have detected this redshift in the light from S2 and other nearby stars. It's another confirmation that something incredibly massive and dense is sitting at the galactic center. Over the years, astronomers have identified dozens of stars in tight orbits around Sagittarius A star. Each one is a natural laboratory, a place where we can test Einstein's theories under extreme conditions. And so far, Einstein has been right every time. But these stars are also in danger. If a star drifts too close to the black hole, if its orbit decays, or if it gets gravitationally nudged by another star, it could cross the event horizon, and then it would be gone, torn apart by tidal forces, its matter spiraling down into the black hole, adding to its mass. This has probably happened countless times over the history of the Milky Way. Stars that wandered too close, that got unlucky. One moment they're there, orbiting like they have for millions of years. The next moment, they've crossed a line in space, and they cease to exist as stars. Let your breathing slow even more now. Feel yourself sinking deeper into rest, and let's explore what it would be like to journey close to Sagittarius A star ourselves. Part 3. A Journey to the Edge. Imagine you're in a spacecraft, falling toward Sagittarius A star. This is just a thought experiment, of course. A gentle story to ease you towards sleep. You've traveled 26,000 light years from Earth. Around you, the stars are incredibly dense. You can see hundreds, thousands of stars in every direction, many of them bright enough to cast shadows inside your spacecraft. The sky is never dark here. It's always glowing with starlight. And ahead of you, at the center of everything, nothing, or at least nothing you can see, just a region of darkness where the stars seem to end. That's where Sagittarius A star waits. As you fall closer, you notice something strange. The stars behind you back toward Earth appear to be shifting. Their light is changing color, becoming redder. That's because you're moving away from them at an ever-increasing speed, falling toward the black hole. The Doppler effect is shifting their light toward the red. Meanwhile, the stars ahead of you are shifting toward blue. You're falling toward them, or at least toward their light. Everything in your field of view is starting to distort. Closer still, and the distortions become more extreme. Light from distant stars is being bent around the black hole. You start to see multiple images of the same star, light that has taken different curved paths through space to reach your eyes. The view becomes strange, dreamlike. The laws of geometry that you've always taken for granted no longer seem to apply. And then you notice the disk. Around the black hole, there's a flat disk of glowing gas. It's called an accretion disk, material that's been captured by the black hole's gravity and is slowly spiraling inward. The disk is incredibly hot, millions of degrees, and it's shining brilliantly in X-rays and other high-energy radiation. But here's the strange thing. The disk doesn't look flat. Because of the way space is curved near the black hole, you can see the top and bottom of the disk at the same time. The disk curves up and over the black hole, wrapping around it in a way that seems impossible. It's like looking at a ring from the side and from above simultaneously. As you continue to fall, time begins to behave strangely. You have a clock on your spacecraft, and you're comparing it to signals from Earth. What you notice is that Earth's signals are arriving faster and faster. Time on Earth, from your perspective, is speeding up. This is gravitational time dilation again. You're falling deeper into the black hole's gravitational well, and time for you is slowing down relative to the rest of the universe. If you could somehow hover here indefinitely, watching Earth, you'd see time passing faster and faster there. You'd watch the sun rise and set in rapid succession, watch the seasons flash by, watch years pass in what feels like days. But you can't hover, not without impossibly powerful engines. Gravity is pulling you inexorably inward. You cross the innermost stable circular orbit. This is the closest you could orbit the black hole without falling in, if you had perfect control of your spacecraft. It's about 3 times the radius of the event horizon. Beyond this point, there are no stable orbits. Everything is falling. The tidal forces are becoming noticeable now. Tidal forces are differences in gravitational pull. The part of your spacecraft closer to the black hole is being pulled harder than the part farther away. If you were falling feet first toward the black hole, your feet would be pulled more strongly than your head. For a stellar mass black hole, the kind that forms from a collapsed star, these tidal forces would be extreme. They'd stretch you and compress you simultaneously in a process that's grimly called spaghettification. You'd be torn apart long before you reach the event horizon. But Sagittarius A star is different. Because it's so massive, its event horizon is enormous. About 17 times the diameter of the Sun. That's big. And because it's big, the curvature of space near the event horizon isn't as steep as it would be for a smaller black hole. The tidal forces are still there, but they're gentler. You could actually cross the event horizon of Sagittarius A star without being torn apart. At least, not right away. And now, You reach it, the event horizon. From the outside, looking in, you'd see something strange. You'd see yourself, or rather, an image of yourself, frozen at the event horizon, redder and redder, dimmer and dimmer, but never quite crossing. That's because the light from the moment you cross takes longer and longer to escape, red-shifted by the extreme time dilation. To an outside observer, you'd appear to freeze in time, fading slowly into darkness. But from your perspective, nothing special happens at the event horizon. You don't feel anything different. You simply cross it and you're inside. Inside the event horizon, everything changes. Space itself is falling into the black hole now, faster than the speed of light, and you're falling with it. You can fire your engines at full power, trying to escape. You can shine a flashlight upward, trying to send a signal out. It doesn't matter. Everything is being pulled toward the singularity at the center. The singularity is where all the mass of the black hole is located. According to general relativity, it's a point of infinite density where space and time break down. Our equations stop making sense there. Our understanding of physics fails. As you fall toward the singularity, the tidal forces grow stronger. Space stretches. Time becomes mixed up with space in ways that are impossible to visualize, and eventually, well, we don't really know. The mathematics says the singularity has zero volume and infinite density, but most physicists suspect that something else happens. Maybe quantum effects take over. Maybe the singularity isn't really infinite, but whatever happens, you wouldn't survive to report back. Once you cross the event horizon, you're gone from the universe forever. Let that image fade now. Let yourself drift back out of the black hole, back to safety, back to the comfortable place where you're resting right now. Take a deep breath and let's continue our story from a safer distance. Here's something remarkable about Sagittarius A star. Despite being a supermassive black hole, despite containing 4 million times the mass of the Sun, it's actually quite quiet. Some supermassive black holes in other galaxies are incredibly active. They're surrounded by enormous accretion disks with vast amounts of matter spiraling in. As that matter falls inward, it releases tremendous amounts of energy. These active black holes can outshine all the stars in their galaxy combined. We call them quasars, or active galactic nuclei, but Sagittarius A star isn't like that. It's relatively calm. It's not consuming much matter at all, maybe the equivalent of a single Earth mass of material per year. That might sound like a lot, but for a black hole, it's barely a snack. Why is Sagittarius A star so quiet? Part of the reason is that it's already consumed most of the easily accessible material in its vicinity. The stars near it are too far away to be captured easily. The gas clouds in the area are relatively thin. There's simply not much material falling in. But Sagittarius A star does occasionally flare up. Astronomers have detected sudden increases in X-ray and radio emissions, lasting for hours or days. These flares might happen when a small amount of gas or a small object falls into the black hole. Maybe a comet gets too close, maybe an asteroid. Whatever it is, it's torn apart and consumed, releasing a burst of energy in the process. One of the most exciting events astronomers observed was the close passage of a gas cloud called G2. In 2014, this cloud came incredibly close to Sagittarius A star. Astronomers were watching carefully, wondering if the black hole would tear the cloud apart and consume it, and if so, what kind of fireworks would result. As it turned out, G2 survived. It was stretched and distorted by tidal forces, but it didn't fall in. Some astronomers now think G2 might not have been just a gas cloud. It might have been a star surrounded by a dusty envelope with enough mass to hold itself together against the black hole's pull. But even though Sagittarius A star is quiet now, it wasn't always that way, and it won't stay quiet forever. Evidence suggests that in the past, Sagittarius A star was much more active. There are structures in the gas around our galaxy called Fermi bubbles, enormous lobes of hot gas extending thousands of light years above and below the galactic disk. These bubbles might have been created by a period of intense activity from Sagittarius A star, perhaps a few million years ago. Imagine what that must have been like. The black hole, fed by some enormous influx of gas or stars, suddenly blazing to life. Jets of high-energy particles shooting out above and below the galactic plane, powered by the immense energy of matter falling into the black hole. The center of the galaxy would have been a dangerous place, flooded with radiation. And then, as the fuel ran out, the black hole quieted down again, returning to its current state of relative calm. Feel yourself relaxing even more deeply now. Your muscles loose, your breathing slow and easy. And as you rest, let's think about the future of Sagittarius A star. Part 4. Collision Course. Our Milky Way galaxy is not alone in space. It's part of a small group of galaxies called the Local Group, and the largest member of the Local Group, even bigger than the Milky Way, is the Andromeda Galaxy. Andromeda is about 2.5 million light years away, and it's moving toward us. Galaxies aren't fixed in place. They move through space, pulled by gravity, and the Milky Way and Andromeda are on a collision course. In about 4 to 5 billion years, they're going to merge. When two galaxies collide, it's not like two solid objects smashing together. Galaxies are mostly empty space. The stars are so far apart that collisions between individual stars are extremely rare. Instead, what happens is that the two galaxies pass through each other, their gravity pulling and distorting them, until eventually they merge into a single, larger galaxy. This has happened before in the history of the universe. It's happening right now in many places. Galaxy mergers are a normal part of cosmic evolution. And when the Milky Way and Andromeda merge, their supermassive black holes will merge too. Andromeda has its own supermassive black hole at its center, even more massive than Sagittarius A star, somewhere between 100 and 200 million times the mass of the Sun. When the two galaxies come together, these two black holes will spiral toward each other, drawn together by gravity. The process will take a long time, millions of years. The black holes will orbit each other, getting closer and closer, until finally they merge in a catastrophic event that will release more energy than all the stars in both galaxies combined. When two supermassive black holes merge, they create ripples in space-time itself. We call these ripples gravitational waves. They travel outward at the speed of light, carrying information about the collision. Gravitational waves from smaller black hole mergers have already been detected here on Earth using incredibly sensitive instruments called interferometers. The merger of Sagittarius A star with Andromeda's black hole will create gravitational waves so powerful that they'll shake the entire cosmic neighborhood. Of course, by shake, I mean tiny distortions in space-time. Nothing that would be dangerous. But it will be an event of immense cosmic significance, and the result? A single, even more massive black hole sitting at the center of the new merged galaxy. A black hole containing several 100 million times the mass of the Sun. But don't worry, this won't happen for billions of years. And by then, the Sun will have evolved into a red giant and swallowed the Earth anyway. The merger of the Milky Way and Andromeda is not something any human will ever witness, unless, of course, our descendants are still around in some form, spread throughout the galaxy, or perhaps beyond, watching as the universe continues its endless dance of creation and destruction. Let that vast timescale wash over you, billions of years, time beyond comprehension. And yet, it's all part of the same universe we live in now, the same laws of physics, the same fundamental forces, just playing out over scales we can barely imagine. Let's zoom out a bit now and think about the broader region around Sagittarius A star. Because the black hole doesn't exist in isolation, it's surrounded by a complex and fascinating environment. The very center of the galaxy is densely packed with stars. Within a single light year of Sagittarius A star, there are millions of stars. For comparison, the nearest star to our Sun, Proxima Centauri, is about 4 light-years away. If Earth were in the galactic center, our night sky would be astonishing. Thousands of stars bright enough to cast shadows. No darkness at all, really. Just a perpetual twilight glow. These central stars are mostly old, red stars. They've been orbiting the galactic center for billions of years, but there are also some young, bright, blue stars, and that's a puzzle. You see, stars form from clouds of gas and dust, and near Sagittarius A star, the tidal forces are so strong that gas clouds should be torn apart before they can collapse and form stars. So how did these young stars get there? One possibility is that they formed farther out, in a more stable region, and then migrated inward. Another possibility is that they formed in a massive disk of gas that temporarily accumulated around the black hole, somehow resisting the tidal forces long enough for stars to condense. The truth is, we're not entirely sure. The galactic center is full of mysteries like this, things that don't quite make sense, that challenge our understanding. There's also a structure called the circumnuclear disk. This is a ring of gas and dust orbiting Sagittarius A star at a distance of a few light years. It's dense and clumpy, with streamers of material falling inward toward the black hole. The circumnuclear disk is probably where some of the material that feeds Sagittarius A star comes from. Though, as we've discussed, the black hole isn't eating much these days. Beyond the circumnuclear disk, there's a larger region called the central molecular zone. This is a vast reservoir of gas, extending for hundreds of light years around the galactic center. It contains millions of times the mass of the Sun in molecular hydrogen, fuel for future generations of stars. The central molecular zone is a stormy, turbulent place. Gas clouds are colliding, shock waves are propagating through the medium, and magnetic fields are twisting and tangling. It's one of the most active star-forming regions in the galaxy. Although most of the star formation happens in clumps and clusters, not uniformly throughout the region. And threaded through all of this are magnetic fields, powerful, complex magnetic fields that guide the motion of charged particles and help shape the structure of the gas. We're only beginning to understand the role these magnetic fields play in the dynamics of the galactic center. Imagine floating through this region, this crowded, energetic heart of the galaxy. Stars all around you, gas clouds glowing with the light of newborn stars, the faint pull of Sagittarius A star at the center of everything. It would be beautiful and terrifying at the same time. But from Earth, 26,000 light years away, it's just a faint glow in the constellation Sagittarius, a patch of light that most people never notice. Even though Sagittarius A star is relatively quiet, it's not completely inactive. And one of the fascinating features astronomers have observed is the presence of magnetic fields around the black hole. Black holes themselves don't have magnetic fields, but the hot, ionized gas swirling around them does. And when this gas moves through a magnetic field, it can create complex and powerful effects. In some black holes, the interaction between the accretion disk and magnetic fields creates narrow beams of particles shot out at nearly the speed of light. These are called relativistic jets. They can extend for thousands or even millions of light years, plowing through intergalactic space like cosmic searchlights. Sagittarius A star doesn't have jets like that, or if it does, they're too weak for us to detect clearly, but there is evidence of magnetic activity. Radio observations have revealed twisted magnetic field lines around the black hole, and there are hints that small-scale outflows might be occurring. Magnetic fields play a crucial role in how black holes accrete matter. The fields can actually slow down the infall of gas, causing it to spiral around the black hole rather than falling straight in. This creates the accretion disk we've talked about, and the fields can also tap into the rotational energy of the black hole itself through a process called the Blandford-Znajek mechanism to power jets and other outflows. It's a beautiful example of how different phenomena in physics are interconnected. Gravity, magnetism, fluid dynamics, relativity, all working together in the extreme environment near a black hole. One thing that scientists are still trying to understand is how black holes spin. You see, black holes can rotate. In fact, most black holes probably do rotate because they form from rotating objects like collapsing stars or merging matter. And the spin of a black hole affects the space around it in profound ways. A spinning black hole drags space itself around with it. This effect is called frame dragging. Imagine stirring honey with a spoon. The honey near the spoon gets pulled along. Space near a spinning black hole behaves similarly, though of course the analogy is imperfect. For Sagittarius A star, astronomers are trying to measure its spin. The shape of the shadow we see in that famous image, and the way matter flows in the accretion disk, can tell us about the black hole's rotation. Early evidence suggests that Sagittarius A star might be spinning relatively slowly compared to its maximum possible spin. But the measurements are difficult, and scientists are still working to refine them. If Sagittarius A star is spinning, that rotation contains an enormous amount of energy. Energy that, in principle, could be extracted and used. Of course, we have no idea how any civilization could actually do that. But it's a fascinating thought. A black hole as a power source, its rotation tapped to fuel an entire galactic civilization. Let your mind rest with that image for a moment. A future so distant it's barely imaginable. And then let it go. Let everything go. Just breathe and relax and continue drifting with me through this story. Part 5. The Cosmic Laboratory. Sagittarius A star serves as a natural laboratory for testing some of the most fundamental theories in physics. Because the environment near the black hole is so extreme, it allows us to observe effects that would be impossible to study anywhere else. We've already mentioned gravitational time dilation and gravitational redshift, effects predicted by Einstein's general theory of relativity. But there are other predictions that Sagittarius A star helps us test. One of these is the precession of orbits. In Newton's theory of gravity, planets orbit in perfect ellipses that remain fixed in space. But in Einstein's theory, the ellipse itself slowly rotates. This effect is called precession. Mercury, the closest planet to our Sun, shows orbital precession. It was one of the first confirmations of general relativity, observed more than a century ago. But the effect is small, just a tiny shift in Mercury's orbit over time. For stars orbiting Sagittarius A star, the precession is much more dramatic. The star S2, which we've mentioned several times, has an elliptical orbit, and that ellipse is precessing noticeably. Astronomers have measured this precession with great accuracy, and it matches the predictions of general relativity almost perfectly. This is important because it shows that Einstein's theory works even in the most extreme gravitational fields we can observe. It's not just a theory for weak gravity, like here on Earth or in our solar system. It's a theory that describes gravity everywhere, even right at the edge of a black hole. Scientists are also using Sagittarius A star to search for deviations from general relativity, because while Einstein's theory has passed every test so far, we know it can't be the complete story. General relativity and quantum mechanics, our two most fundamental theories, are incompatible with each other. At some level, probably at extreme scales of energy or curvature, general relativity must break down or need to be modified. So, astronomers watch Sagittarius A star carefully, measuring everything they can, looking for any tiny anomaly, any hint that something doesn't match Einstein's predictions. So far, they haven't found anything, but the search continues. There's also the question of whether black holes are truly black. Stephen Hawking predicted that black holes should emit a very faint radiation, now called Hawking radiation. This radiation comes from quantum effects near the event horizon. It's incredibly faint, far too faint to detect from Sagittarius A star with our current technology. But if we could detect it, it would be a profound discovery, connecting quantum mechanics and gravity in a way we've only theorized about. For now, Hawking radiation remains theoretical, but Sagittarius A star is there, waiting, a cosmic laboratory, patiently allowing us to probe the nature of reality. Let that patience settle into you now, the patience of the universe, time moving slowly, steadily, no rush, just the gentle unfolding of natural laws. The Milky Way isn't special. Almost every large galaxy we've observed has a supermassive black hole at its center. This seems to be a fundamental feature of how galaxies form and evolve. Some of these black holes are much larger than Sagittarius A star. In the galaxy M87, about 55 million light-years away, there's a black hole containing about 6.5 billion times the mass of the Sun. That's more than 1,000 times more massive than Sagittarius A star. M87's black hole was actually the first supermassive black hole ever imaged. In 2019, the same international team that later imaged Sagittarius A star released a picture of M87's black hole. It showed the same features, a bright ring of light surrounding a dark shadow. But because M87 is so much farther away, and because its black hole is so much larger, the image was actually easier to capture in some ways. M87's black hole is also much more active than Sagittarius A star. It has a powerful jet, a beam of particles shooting out from near the black hole at almost the speed of light. This jet extends for thousands of light years into space, visible in both radio and optical wavelengths. It's one of the most spectacular structures in the nearby universe. Why is M87's black hole so active when Sagittarius A star is so quiet? Probably because M87 has more available fuel, more gas in its central regions, perhaps fed by interactions with other galaxies. The black hole is being fed, and it's converting that mass into energy, powering the jet. Then there are the quasars. These are supermassive black holes in the distant universe, billions of light years away. When we look at quasars, we're seeing them as they were billions of years ago, when the universe was younger. And what we see is astonishing. These ancient black holes are surrounded by enormous accretion disks, blazing with the light of 1 trillion suns. They're the brightest sustained sources of light in the universe. Some quasars are so bright that we can see them from halfway across the observable universe. Quasars tell us that in the early universe, supermassive black holes were much more common and much more active. There was more gas available, more mergers happening, more chaos. The universe was a more violent place. As time passed, galaxies settled down. The gas got used up, turned into stars. The mergers became less frequent, and the black holes, having consumed most of the easily available matter, quieted down. Sagittarius A star today is like a retired quasar, a once mighty engine now running on idle. But every galaxy's black hole has a story. Some are still feeding actively, like M87. Some are completely dormant, with no accretion disk at all. Some are in the process of merging with another black hole, locked in a gravitational dance that will take millions of years to complete. And at the center of each one is the same strange object, an event horizon, a singularity, a region where space and time break down. The same physics playing out in countless variations across the universe. Sagittarius A star doesn't just sit passively at the center of the Milky Way. It influences the galaxy around it in subtle but important ways. One way it does this is through something called feedback. When a black hole is actively accreting matter, it releases enormous amounts of energy. This energy heats the surrounding gas, preventing it from cooling and collapsing to form stars. In some cases, the energy can even blow gas out of the galaxy entirely. This feedback mechanism is thought to be crucial in regulating the growth of galaxies. Without it, galaxies would form stars too quickly, using up all their gas in a relatively short time. The black hole acts as a kind of thermostat, controlling the star formation rate and keeping the galaxy in balance. Right now, Sagittarius A star is too quiet to have much feedback effect, but in the past, when it was more active, it would have played this regulatory role. And in the future, if it starts accreting matter again, it will once more influence star formation in the galactic center. There's also a more direct influence. The gravity of Sagittarius A star, while not strong enough to significantly affect objects at Earth's distance, does shape the orbits of stars in the central region. It creates a gravitational potential well that all those stars are moving through. The orbital dynamics of the entire central star cluster are determined by the black hole's mass. Interestingly, there's also a relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. More massive galaxies tend to have more massive black holes. This relationship suggests that black holes and galaxies grow together, co-evolving over billions of years. We don't fully understand why this relationship exists, but it points to a deep connection between the largest structures in the universe, galaxies, and the most extreme objects, supermassive black holes. In a sense, Sagittarius A star is both the product and the sculptor of the Milky Way. It formed from the dense matter at the galaxy's center, growing over time. And as it grew, it influenced the galaxy's evolution, regulating star formation, shaping the distribution of matter. The galaxy and the black hole locked in a cosmic partnership. Feel yourself sinking deeper into rest now. Your body is heavy, comfortable. Your mind is quiet, just following along with these ideas, these images. No effort needed, just listening and drifting. Part 6. The quest for understanding. Throughout this journey, we've talked about what we know about Sagittarius A star, but it's worth taking a moment to appreciate how much we don't know, how much mystery still remains. We don't fully understand how supermassive black holes form. We don't know exactly how they grow. We don't know what happens at the singularity, where our equations break down. We don't know if there are other objects in the universe that could masquerade as black holes, or whether black holes are truly the only explanation for what we observe. We don't understand the detailed physics of accretion disks, especially in the turbulent, magnetized environment near a black hole. We don't know how jets form or what determines their power. We don't know how common it is for black holes to capture and destroy stars, or what that process looks like in detail. And there are deeper questions about the nature of space and time, questions about what it means for something to exist inside a black hole, questions about whether information is truly lost when something falls past the event horizon, or whether it's somehow preserved. These questions touch on the foundations of physics. They're not just about black holes. They're about the nature of reality itself. And Sagittarius A star, sitting there at the center of our galaxy, is one of the key places we look for answers. Every generation of astronomers brings new tools to bear on these questions. Better telescopes, more sensitive detectors, more sophisticated computer simulations. Each advance reveals new details, raises new puzzles, pushes our understanding a little further. The image of Sagittarius A star released in 2022 was a triumph, but it's not the end of the story. It's just one chapter. Future observations will probe the environment around the black hole in even greater detail. They'll measure its spin more accurately. They'll watch how matter flows in the accretion disk. They'll search for gravitational waves from merging black holes elsewhere in the universe. And perhaps someday we'll develop a complete theory of quantum gravity, a theory that unites general relativity and quantum mechanics, that tells us what really happens at the singularity. When that day comes, Sagittarius A star will be one of the places we look to test that theory. For now, though, it remains mysterious. A dark heart at the center of our galaxy, a place where the rules are different, a cosmic riddle that we're only beginning to solve. Let that sense of mystery rest gently in your mind. Not something to worry about or puzzle over, just mystery, the unknown, the vast space of all the things we have yet to learn. It's beautiful in its way, comforting. There's always more to discover. Let's think about scale for a moment, because one of the most mind-bending aspects of Sagittarius A star is how it challenges our intuitions about size and distance. The event horizon of Sagittarius A star is about 12 million miles across. That sounds enormous. And it is. It's about 40 times the diameter of the Sun. If you replace the Sun with Sagittarius A star, the event horizon would extend out beyond the orbit of Mercury. But remember, this event horizon contains 4 million times the mass of the Sun. All that matter, compressed into a region that, while large by everyday standards, is tiny on cosmic scales. Now zoom out. The Milky Way galaxy is about 100,000 light-years across. Sagittarius A star sits at the center, which is 26,000 light-years from Earth. That's the distance light travels in 26,000 years. It's so far that the light we see from the galactic center today left there before humans invented agriculture. But Sagittarius A star itself? Its event horizon is about 12 million miles, which is only about 12 light seconds across. In the time it takes light to cross the event horizon of Sagittarius A star, it could circle the entire Earth about 20 times. So, The black hole is massive in terms of its gravity and its influence, but physically, it's a tiny speck in the vastness of the galaxy. Now, zoom out further. The Milky Way is just one galaxy among hundreds of billions in the observable universe, and almost all those galaxies have supermassive black holes at their centers. Each one a dark heart, a gravitational anchor shaping the galaxy around it. The observable universe is about 93 billion light-years across. Within that volume, there are an estimated 100 million supermassive black holes, some larger than Sagittarius A star, some smaller. Each one a unique object with its own history, its own story. And yet, despite how common supermassive black holes are, each one represents something extreme. A place where matter has been compressed beyond the point of any normal structure, where the fabric of space-time is so warped that our understanding begins to fail. Think about that. The universe is full of these extreme objects. They're not rare, exotic anomalies. They're fundamental components of galaxies, and yet they're still profoundly strange. Let your mind expand to hold these scales, not straining, just gently expanding. 12 light seconds, 26,000 light years, 100,000 light years, 93 billion light years. Numbers so large, they lose meaning. And yet, they're all part of the same universe, the same reality that includes you, resting comfortably right now. Let's return once more to those stars orbiting Sagittarius A star, because their stories are worth dwelling on. Imagine you're a star, born in the galactic center 10 million years ago. You formed from a collapsing cloud of gas, like all stars do. Nuclear fusion ignited in your core, and you began to shine. Around you, thousands of other stars, all crowded into a relatively small space. Your orbit around Sagittarius A star takes you in a long, elliptical path. Sometimes you're close to the black hole, just a few light days away. Other times, you're farther out, light months distant. Your orbital period might be hundreds or thousands of years. Over the course of your life, you pass by countless other stars. Occasionally, you come close enough to one that your orbits are perturbed. Your path around the black hole shifts slightly. This has happened many times over your 10 million year existence. Each encounter, a tiny change. But over time, these changes add up. Some stars aren't so lucky. They come too close to another star or to the black hole itself. Their orbits decay, they spiral inward, and eventually, they cross the event horizon. You've witnessed this happen. Not that you could see it in any human sense, but the gravitational effects are there. A neighboring star, one you've shared this crowded space with for millions of years, suddenly gone. Its light winking out as it approaches the event horizon, red-shifted and dimmed until it fades to nothing. You, though, you've been lucky. Your orbit has remained stable. You haven't been ejected from the galactic center, flung outward by a close encounter. You haven't fallen into the black hole. You've found a balance, a stable path through this gravitational minefield. But your life as a star is finite. Eventually, you'll run out of fuel. If you're a massive star, you'll explode as a supernova, scattering your matter back into space. If you're a smaller star like our Sun, you'll expand into a red giant and then collapse into a white dwarf. Whatever happens, your matter will remain in the galactic center. It will become part of the gas and dust that swirls around Sagittarius A star, and perhaps millions of years from now, that matter will fall into the black hole. You'll add your mass to its mass, contributing to its growth. Or perhaps your matter will be incorporated into a new generation of stars, the cycle continuing as it has for billions of years. Birth, life, death, rebirth. The endless dance of matter and energy in the cosmos. Let yourself feel a sense of peace with that cycle. Nothing is permanent, but nothing is truly lost either. Everything transforms again and again, taking on new forms. Even the matter that makes up your body right now was once part of stars. You're made of stardust, as the saying goes. And someday, that matter will become something else. Part 7. What we can't see. For all our observations and theories, there's so much about Sagittarius A star that remains hidden from us. Not just unknown, but perhaps unknowable, at least with our current understanding. The most obvious example is the singularity itself, the point at the very center of the black hole where, according to general relativity, all the mass is concentrated. Our equations say that at the singularity, density becomes infinite, space-time curvature becomes infinite. The normal rules of physics break down completely. But most physicists don't believe the singularity is truly infinite. They suspect that when we develop a theory of quantum gravity, we'll find that something else happens. Maybe the matter doesn't collapse to a point, but to some tiny but finite size. Maybe there's a quantum bounce, or a connection to another region of space-time. Maybe something even stranger that we haven't imagined yet. The problem is, we can't observe the singularity. It's hidden behind the event horizon, and according to general relativity, nothing that happens inside the event horizon can ever send a signal out. The singularity is, by definition, cut off from the rest of the universe. This leads to deep questions about the nature of reality. If something exists but can never be observed or influence anything outside itself, does it exist in any meaningful sense? If information falls into a black hole and can never be retrieved, is it truly lost? These aren't just philosophical questions. They're questions about the fundamental laws of physics. Because in quantum mechanics, information is supposed to be conserved. It can't just disappear. But if information falls into a black hole and is destroyed at the singularity, that conservation law would be violated. This puzzle is known as the black hole information paradox. Stephen Hawking spent decades working on it, and his ideas evolved over time. He initially argued that information was indeed destroyed. Later, he came to believe that information might be preserved in subtle ways, perhaps encoded in the Hawking radiation that black holes theoretically emit. The debate continues. Some physicists believe information is preserved. Others believe it's lost. Still, others believe the question is ill-posed, that we're thinking about it in the wrong way. Sagittarius A star sits there, silent, keeping its secrets. There's also the question of what happens to time inside a black hole. We know that from the perspective of an outside observer, time appears to stop at the event horizon. But what about from the perspective of someone falling in? According to general relativity, you'd experience time normally as you fell toward the singularity. The universe outside would seem to speed up dramatically, but your own clocks would tick normally. And then, well, we don't really know. Time might end at the singularity, or it might continue in some strange way we can't currently describe. These are the deep mysteries, the questions that keep physicists awake at night, or perhaps lull them to sleep with wonder. And Sagittarius A star, our nearest supermassive black hole, is the closest laboratory we have for probing them. Let those mysteries rest gently in your mind. No need to solve them, just acknowledge them. The universe is full of things we don't understand, and that's okay. It's beautiful, even. Here's something poetic to contemplate. Sagittarius A star makes sound, or at least it creates ripples that could be interpreted as sound if you translated them in the right way. In 2003, astronomers discovered that the black hole at the center of the Perseus galaxy cluster was creating pressure waves in the hot gas surrounding it. These waves are technically sound waves, though they're at a frequency far, far below what human ears can hear. The note, if you could hear it, would be a B flat, about 57 octaves below middle C. For Sagittarius A star, similar processes might be at work. The black hole, as it accretes small amounts of matter, creates disturbances in the surrounding gas. These disturbances propagate outward as waves. They're not sound in the normal sense. Space is a vacuum, and sound as we know it can't travel through a vacuum. But in the thin gas around the black hole, pressure waves can propagate. And then there are gravitational waves. These are ripples in space-time itself, created by accelerating masses. When two black holes merge, they create powerful gravitational waves. But even a single black hole, if it's accreting matter in an asymmetric way, might create weak gravitational waves. Gravitational waves travel at the speed of light. They pass through everything: planets, stars, even other black holes. They carry information about the events that created them, encoded in their frequency and amplitude. In 2015, for the first time in history, gravitational waves were detected directly here on Earth. The waves came from two stellar mass black holes merging over 1 billion light-years away. Since then, dozens more gravitational wave events have been detected. Someday, we might detect gravitational waves from events involving supermassive black holes. Maybe from Sagittarius A star accreting a star. Maybe from distant supermassive black holes merging. These waves would have much lower frequencies than the ones we've detected so far, requiring different kinds of detectors. When we do detect them, we'll be listening to space-time itself, hearing the vibrations of the cosmic fabric. The universe has a soundtrack, inaudible to human ears, but real nonetheless. And Sagittarius A star is one of the instruments playing in that vast cosmic symphony. Let that image settle. The universe, singing. Black holes, playing their deep, resonant notes. Gravitational waves, rippling outward through space and time. All of it connected, all of it part of the same grand performance. We've been focusing on Sagittarius A star, but let's zoom back out and think about our own relationship to it. Because even though we're 26,000 light years away, we're still connected to the galactic center in meaningful ways. Our sun, our entire solar system, is orbiting Sagittarius A star. We're moving through space at about 500,000 miles per hour, swept along in the galaxy's rotation. It takes us about 230 million years to complete one orbit. The last time we were in this position in our orbit, dinosaurs were just beginning to emerge on Earth. So, in a very real sense, Sagittarius A star is the anchor point of our cosmic journey. It's what we're orbiting around. It's the gravitational center that holds our galaxy together. But we're also incredibly safe from it. At our distance, the black hole's gravity is no stronger than the gravity of all the other stars and dark matter in the galaxy. We're not being pulled towards Sagittarius A star any more than we're being pulled in any other direction. We're in a stable orbit, and will remain so for billions of years. Even if Sagittarius A star were suddenly turned off, if it vanished somehow, it wouldn't dramatically affect us. The galaxy might become slightly less gravitationally bound, but the changes would be gradual. We'd continue on much as before. And yet, knowing that Sagittarius A star is there, knowing what it is, changes how we see the universe. It reminds us that the cosmos operates on scales and with phenomena that dwarf human experience. It reminds us that the universe is stranger, more extreme, more wonderful than we ever imagined. Looking up at the night sky, even though we can't see Sagittarius A star directly, we can think about it, we can know it's there, and we can feel a sense of connection to it. Not a physical connection, but an intellectual and emotional one. We're part of this galaxy. We're made of matter that has been cycling through the galaxy for billions of years. Some of the atoms in your body might once have been closer to the galactic center. They might have been part of a star that lived and died in that crowded region. They've traveled a long journey to become part of you, and after you, they'll continue their journey. Someday, far in the future, those atoms might find their way back to the galactic center. They might become part of the gas around Sagittarius A star. They might even fall into the black hole itself, adding their tiny contribution to its mass. In that sense, we're all connected to Sagittarius A star. We're all part of the same cosmic dance, the same great cycle of matter and energy that has been unfolding since the beginning of time. Let that thought bring you comfort. You're part of something vast, something ancient, something that will continue long after you're gone. You're a temporary pattern in the cosmic flow, a brief eddy in the stream, but you're real, and you're here, and you're connected to everything. Part 8. The future awaits. We're approaching the end of our journey now. But before we finish, let's think about the future. What lies ahead for Sagittarius A star? In the short term, which in cosmic terms means the next few billion years, Sagittarius A star will probably remain much as it is now, relatively quiet, occasionally flaring when it captures a small amount of matter, gradually growing as it accumulates gas from the surrounding region. The stars in the galactic center will continue their orbits. Some will fall in, others will be ejected. New stars will form from the gas in the central molecular zone. The dance will continue. Then, in about 4 billion years, the Andromeda Galaxy will arrive. The two galaxies will merge, and their supermassive black holes will begin the long process of spiraling together. This will take millions of years, but eventually Sagittarius A star and Andromeda's black hole will merge into a single, more massive object. The merger will release an enormous burst of gravitational waves. It will shake the newly formed galaxy, and when it's over, a new supermassive black hole will sit at the center of the merged galaxy. A black hole several 100 million times the mass of the Sun. That black hole might be more active for a while, fed by gas that's been stirred up by the merger. It might shine brightly, perhaps even becoming a quasar temporarily. And then, as the gas settles and gets used up, it will quiet down again. But what about the truly distant future? Trillions of years from now, eventually, all the stars will burn out. The universe will become a dark, cold place. Galaxies will disperse. Black holes will be the last large objects remaining, slowly evaporating through Hawking radiation. The evaporation process is incredibly slow. For a black hole the size of Sagittarius A star, it would take about 10 to the 99th power years. That's a 1 followed by 99 zeros, far, far longer than the current age of the universe. But eventually, even Sagittarius A star will evaporate. It will shrink slowly as it emits Hawking radiation, and then, in a final burst of energy, it will vanish. All the mass it ever accumulated, all the stars and gas it ever consumed, all the information that ever fell into it, will be returned to the universe as radiation, spread out, diluted, dispersed into the void. And the spot where Sagittarius A star once sat, the heart of the Milky Way, will be empty. Just empty space in an empty universe, cold and dark and nearly eternal. It's a sobering thought, but it's also, in its way, peaceful. Everything has its time. Stars live and die. Black holes form and evaporate. Even the universe itself may eventually end or transform into something else. Nothing lasts forever, but while it exists, it's real. It matters. Sagittarius A star exists now. It has existed for billions of years, and it will exist for billions more. That's enough. We've covered so much ground tonight, from the discovery of Sagittarius A star to its nature as a supermassive black hole, from the stars that orbit it to the extreme physics near its event horizon, from its past to its far future. But perhaps the most remarkable thing isn't Sagittarius A star itself. Perhaps it's the fact that we humans, tiny creatures on a small planet in an obscure corner of the galaxy, have been able to figure all this out. We can't see Sagittarius A star directly, at least not easily. We're 26,000 light years away, and yet, through careful observation, through mathematics, through physics, through decades of patient work by thousands of scientists, we've pieced together its story. We've measured its mass. We've tracked the orbits of stars around it. We've imaged its shadow. We've tested our theories against its behavior. We've come to understand, in a deep and meaningful way, what lies at the center of our galaxy. This is one of humanity's great achievements, not building monuments or conquering lands, but understanding the universe we live in, figuring out how things work, even when those things are almost incomprehensibly strange. And we did it driven by nothing more than curiosity, by the simple desire to know what's out there, what's at the center of the Milky Way. How does a black hole work? What happens near an event horizon? These questions don't have practical applications, at least not in any immediate sense. Understanding Sagittarius A star won't cure diseases or solve social problems, but we ask these questions anyway, because we're curious, because we want to know, because the universe is fascinating, and we're part of it, and understanding it helps us understand ourselves. That curiosity is a gift. It's one of the things that makes us human, and every time we answer a question, every time we figure something out, we're celebrating that gift. We're adding to the sum of human knowledge, building on the work of everyone who came before us, and creating foundations for everyone who comes after. So tonight, as you drift towards sleep, you can take pride in being human, in being a creature that asks questions, a creature that wonders, a creature that looks up at the stars and thinks, I want to understand. Our journey is coming to an end. We've traveled 26,000 light years to the very heart of the Milky Way. We've explored Sagittarius A star, the supermassive black hole that anchors our galaxy. We've learned about its discovery, its nature, its influence. We've thought about extreme physics, time dilation, event horizons, singularities. We've imagined what it would be like to fall toward a black hole. We've contemplated the lives of stars in that crowded, dangerous region. We've looked ahead to the distant future when Sagittarius A star will merge with another black hole and then, far later, slowly evaporate away. And through it all, we've marveled at the strangeness of the universe, at the power of human curiosity, at the connection between us and the cosmos. Now, as you settle deeper into sleep, let these images rest in your mind. The ring of light around Sagittarius A star, the stars racing in their orbits, the curved fabric of space-time, the slow, patient work of science, piecing together the cosmic puzzle. Let them become part of your dreams. Let them carry you gently into sleep, like a spacecraft drifting through the darkness between stars. Remember that you are safe, you are comfortable. You are 26,000 light years from Sagittarius A star, in a quiet corner of the galaxy where planets can form and life can flourish. The black hole is there, anchoring everything, but it poses no threat to you. It's simply there, a natural part of the cosmos, a feature of the universe we call home. And remember that the universe is vast, so vast that even our galaxy, with its hundreds of billions of stars, is just a tiny speck in the cosmic ocean. And yet, within that vastness, patterns emerge. Laws govern the behavior of matter and energy. Black holes form in predictable ways. Stars orbit according to mathematical principles. Even in the chaos, there is order. That order is beautiful. It's comforting. It means the universe makes sense, Maybe not in ways that are obvious or intuitive, but it makes sense. It follows rules, and we can figure out those rules if we're patient and clever and curious. Let's think once more about time, about the rhythms that govern the universe. The star S2 completes its orbit around Sagittarius A star every 16 years. Right now, somewhere in that crowded region near the galactic center, S2 is moving through space, following its elliptical path. In a few years, it will reach its closest approach to the black hole, whipping around at 3% of the speed of light, and then it will swing back out, beginning the long journey to the far side of its orbit. This has been happening for millions of years. S2 orbiting 16 years, again and again, a cosmic clock ticking away in the darkness. Our sun orbits more slowly, 230 million years for one complete revolution. When the sun was last in this position in its orbit, the continents on Earth were still joined together in the supercontinent Pangaea. Life was mostly in the oceans. The first dinosaurs were just appearing. One galactic year from now, if Earth still exists, what will life be like? What creatures will walk on the surface, if any? Will humanity still be around, in some form? Or will we be long gone? Our cities crumbled to dust. Our species evolved into something else, or extinct? We can't know. But the galaxy will continue its rotation. The stars will continue their orbits. Sagittarius A star will continue its patient existence at the center of everything. These rhythms are eternal, or close to it. They operate on timescales so vast that human civilizations rise and fall in what is, cosmically speaking, the blink of an eye. And yet, the rhythms are real. They're happening right now, as you rest here. The galaxy is turning. The stars are moving. Sagittarius. A star is sitting at the center, its gravity reaching out across thousands of light years, holding everything in its gentle grip. You are part of this rhythm. Your body is made of atoms that have been cycling through the galaxy for billions of years. Your atoms have their own rhythm. Electrons orbiting nuclei, molecules vibrating, cells dividing and dying and being replaced. Faster rhythms nested inside slower ones. All of it connected, all of it part of the same cosmic dance. Let yourself feel that connection now, not as an abstract idea, but as something real. You are stardust, temporarily organized into the pattern that is you. And when your pattern dissolves, the stardust will remain, ready to form new patterns. That's not something to fear. It's the natural order of things, the rhythm of the universe. Closing. And so, our journey to the center of the Milky Way comes to an end. We've traveled across 26,000 light years, explored the mysteries of Sagittarius A star, and touched the edges of what we know and what remains unknown. As you drift into sleep now, let these cosmic wonders fade gently from your mind. The supermassive black hole sits quietly at the galactic center, as it has for billions of years. The stars continue their orbits. The universe unfolds according to its ancient rhythms. And you are safe, comfortable, connected to it all. part of the same stardust, the same cosmic story. Sleep well. Dream of distant stars, of curved space-time, of the beautiful mysteries that lie at the heart of our galaxy. The universe is vast and strange and wonderful, and you are part of it.